One thing I did this week that was really important, shockingly important, in fact. I mean, normally when I build experimental programming languages, I cannot be arsed to add a syntax for comments. But if what we are doing is writing compilers, then comments are absolutely vital, because the action is in the design. You know, the crucial thing to making the compiler work is that we know what the deal is. So, for example, let me find integer expressions are here. I just put the whole compiler in the document. I added comment syntax so I could say, this is the deal. We need to know the frame height, the initial value of SP minus BP. We need to know the exit point, what to do afterwards. Whoever invokes this compiler is promising us that SP really is H above BP. We promise them that when we jump to the end, BP will not have moved. SP will be back to being H above BP. The value will be in FI. The stack below the current stack frame is going to be as it was. And we also have to document that we don't make any other promises, right? We might trash the other registers. And that means, that's a way of saying, don't trust the contents of other registers to survive the code generated by this compiler. Other registers are not a safe place to keep stuff. So if you document this deal, then as you work through the cases of the compilation process that you need, you know what you can rely on and what your obligations are. And without those comments, it's, you know, if you just keep that stuff in your head, then it's much easier to make mistakes. And if you're thinking, why is this deal, which is goodness knows how many lines of words, why is this just a comment? Why are we not able to express in our programming language what this deal is and have the machine actually check that we are keeping our promises? Then you have very sound instincts. That's exactly what we should be doing. But for the moment, we are simply writing down the promises we expect to be given and the promises that we give in return. So yes, having added comment syntax to the language for writing compilers, I then went and added copious comments to the compiler itself. So hopefully, and I copied the compiler for imp as an appendix to this document about the compiler language. I asked you to think about while, and I'm wondering, yes, here's mine. So, zooming out, that was if. Let's see if we can figure out how to compile while. It always kicks off like this. Right, so we are given a while command. We have our Boolean expression and we have our command, that is the loop body. we have our current frame height, which we are promised, telling us that the height of SP above BP, and we have the exit point that we hope to reach if we're lucky enough that this loop actually stops, which of course it might not. So, what's the first thing we need to do?
Start.
Yeah. Well, yeah. So there's going to be some code at start. What's it going to do?
Evaluate the Boolean.
It's going to evaluate the Boolean expression. So we need to stick in the code that compiles BE. We have to tell it its frame height, which is h. And then we need to say what its exit point is. Well, yeah, we're going to need to put in some code that tests the result of that Boolean. So we're going to create a little code block. We'll call it test. And we'll say, when we've evaluated the Boolean expression, we want to go to test. Okay? So we know we are promised by the compiler for Boolean expressions two things. We are promised, at least two things. We're promised that the flag will have been set or cleared according to the Boolean expression. And we're also promised that the frame height hasn't been messed up. So we are now free to make a conditional. So if the flag has been set, what will we need to do? Yeah, well, yeah, we'll need to run the loop. So yeah, so we're going to have to stick in something that actually runs CM. Let's call that loop. And we'll say what it is in a moment. Oh, sorry, this should be IP is loop. Okay. What should we do if the flag is clear and this jump does not happen? Yeah, we could perfectly well give end as the exit point for that code block, because if the flag was not set by the test, we're done here, the loop's over. Okay? So now we need to say how to run the loop. Okay? And that's going to be the code generated by the command. We need to say what the frame height is, but assuming that the thing which executed the Boolean expression kept its promise to preserve the frame height, then we know what the frame height is. It's still h. Now, what shall we give as the exit point for the loop body?
Start test.
I'm hearing two guesses: start and test. Any opinions? Start. We actually have to. We actually have to run the Boolean expression again to see if it has become true. And if we put test in there, then we'd be saying, oh, let's just pile into this conditional jump, when we have no idea what the last thing was that was monkeying with the flag. So, yeah, so we do have to run the Boolean again, and we do need to be sure what is controlling the flag for this conditional jump. And that's it. Now, you'll notice a weird thing where we're saying, down the left-hand side here, we are saying what our entry points for our compilation tasks are, and yet we use test as an exit point in the definition of start, and we use start as something we can get our hands on in the implementation of loop, and we use loop as something we already can get our hands on in the implementation of test. Yep.
Don't you need semicolons at the labels?
I need semicolons there and there. Thank you for the reminder. Yeah, so we've got this situation where, and it's not actually surprising when you have a loop that there's going to be a loop. So how is it possible that we can resolve this apparent cyclic dependency in the use of these labels? I could tell you it's magic, but it's not. Magic is misdirection, and what's going on here is merely indirection. So don't think of this as a process that happens in this order, or even in this order. It's actually more sensible to read it from left to right. On the left here, we're promising that start and test and loop will, in the fullness of time, refer to addresses of lumps of code. We know these things will be brought into existence. So what we can do is create placeholders. It's the same trick that we did when we were doing type synthesis and we didn't know what a type was. We just made, the machine makes a placeholder that stands for the thing it doesn't know yet and uses that instead. And eventually, once all the code blocks have actually been put into memory, we know the values of all of those placeholders, and we can go back and swap the actual thing for the placeholder. So what's really going on is a two-pass process. First of all, we generate a load of code that's got labels in it, standing for the addresses of things that haven't been put into memory yet. And once we have that code, we know how big everything is, which means we can figure out where to put it in memory. And once we've figured out where to put it in memory, we could replace all the labels by the actual addresses. So we're using a notation. By that process, we're freed up from worrying about exactly what time things happen in the compilation process. It's actually a two-phase process, but we just have to write down the logic of it, not the two phases separately. That's why. That's just one of the reasons I bothered building this language, was to free us up from being explicit about that two-phase process. So you can just say, what's the logic of the code that we're trying to generate? And what was hilarious as I was building it was that I didn't quite get the logic of replacing the placeholders by the actual things right in the first instance, and that meant that the compiler interpreter itself went into an infinite loop while trying to compile a loop. So that was embarrassing. Okay, so we've looked at these things. We should do some of the base cases, like how do we even compile a variable? So somebody gives us an integer expression which consists of a variable. We know the frame height, we know the exit point. What's that going to turn into? There's going to be some code at start. We're pretty sure it's going to be a code block because we haven't got any sub-expressions. Right. We know we've got to put the value of this thing in the first register. That's the deal. So we're pretty sure that we're going to start like that. And now we need to figure out where the hell x is. And that means, it's all right, let's just get the status of this thing correct. X is a meta variable which stands for a program variable. Right? You've got to get this, when you're writing compilers, you've got to get straight in your head which variables are variables that live in the compiler and stand for bits of code, and which variables are actually in the program being compiled. So X is a compiler variable that stands for a program variable. And we're explaining how to compile all the lookups of program variables, not just the ones that happen to be called X. Okay, so we know the symbol table ought to be able to tell us what on earth X is. And the symbol table maps program variables to accessors, and an accessor is the thing that we can put on the right-hand side of an assignment. So there has to be a way of extracting that information from the symbol table, and there is. That's the feature of this compiler language called lookup. So we say lookup X, and that means whatever variable X is, find it in the symbol table and put that accessor in here. So that's where this is where the BP plus H thing, here's where stuff goes into the symbol table, and then here's where it comes out again. Yep?
Can it not find it? Could there be a case where it looks it up and it doesn't find it?
You are quite right. What happens if we use a variable that is not in scope? Very good question. If it's not in scope, then it will not be in the symbol table, and then we will report an error. If we can't find it, that's a mistake. And it's a mistake in the program that we are compiling. Okay? Of course, it's the same deal for compiling an assignment, only slightly more long-winded. How do we do an assignment? Well, first of all, we better evaluate the expression on the right-hand side. So we generate code for IE, same frame height, and then I'm going to call this store. We'll need a code block that actually does the storing. Right. And by the time we get here, we know that the value of that expression is going to be in the first register. So we can play the same game the other way around. We can say lookup X is assigned first register and exit via the shop. Sorry, it's a museum. In museums you always exit via the shop. It's just, so part of the deal is, right, we know part of our promise ought to be that, if the program is going to finish at all, it is going to end up at the required endpoint. No matter what it does, it's got to end up there. Oh, whoops, yes, I forgot that. Go to end there. My bad.
Yeah, okay, that's fine.
Okay, so we've looked at edited highlights of lots of these things. I'm going to do lambda calculus. The lambda calculus compiler is much shorter, by the way, but it's also much weirder. So there's some. there's not very much of it, but there are some interesting ideas that are quite different from the way IMP works, as you'd expect, because they're quite different things. In particular, in the lambda calculus, you know that values are functions. So how the hell do we deal with that? Once we've turned functions into lumps of code, well, we're actually going to be flinging addresses of pieces of code around as actual data. But how else could we do it? So there's some fun to be had there. So this document actually describes the components of a compiler. Basically, there are three things in a compiler in this language. You have to write the grammar of the language you're compiling. You have to write the compilation schemes explaining how to compile each different sort of thing in the grammar and each different production of it. You'd expect that. Otherwise, you could write things down that were in the grammar but not compiled. And you have to say how to start. That's to say, you say which syntactic category the whole program lives in, and you say how to get hold of the entry point for the whole program. And so you have to say, when you get a source code file, which grammatical non-terminal you should use to parse it, how to compile that thing, and how to find where the compiled code should run starting from. So that's pretty much all there is to it. So this document just works through that whole story, so we end up with a situation where a program like that. Yes, so I decided I would actually throw in the ability to define functions as well as just having these expressions and commands. So I worked through that. That turns into a lump of machine code like this, which of course is not terribly edifying, especially when it's on a document camera. But it's interesting to look at the source code, the compilation schemes, and the assembly language that came out, so you can say, oh, I can see this is what came from that. So I'm hoping that real soon now, I will have this technology in a form where I can let you play with it, where you can really just write, take a compiler, take a program, and say, eat that. What do you make of it? Run the resulting code, and then you can tinker away to your heart's content. Okay, let's stop there. There's a box for 1-minute papers.